Hi, now let's solve a numerical example to estimate the equivalent circuit of induction machines using Locked-Rotor and no-load test. So here we have a 30 kilowatt 50 hertz delta connected 405 to 15 volts line-to-line three-phase machine, and we have now the results for the Locked-Rotor, and I will show the no load test results in a minute. So now let's use that Locked-Rotor test. So when we lock the rotor and we don't let it run, so it is stationary, we are applying 6.4 kilovolts. When we apply 130 line voltage, remember we don't apply rated voltage at Locked-Rotor in order not to damage the machine. We apply a smaller voltage, and it's already drawing quite a large current. Okay, so let's try to estimate that one. So, and the resistance between two lines, so that means you have three terminals coming out of the machine, and you connect an ohm meter between two terminals, and you are measuring 0.293 ohms. Okay, so let's try to calculate that one. So let me hide myself. Right, so let's start with that resistance value. Okay, so remember it is a delta connected machine. Okay, and let's say you have, it's just connecting a ohm meter. So if let's say one of those things are R1, okay, R1 is the phase resistance. Okay, and another confusion, actually let me draw the equivalent circuit to here, right? So that branch first. So you have RC, you have XM, you have R1, have J, X1 or X1, but then you have J2 prime referred value, then you have R2 prime over S, and this is my. So one confusion is, again, that is not a real circuit. Okay, that is the equivalent circuit just we used to represent the induction machine, but you need to know the actual differences. So in an induction machine, actually if you connect a ohm meter between these two terminals, and if you just stick to that equivalent circuit, you may think that once I connect a multimeter here, I will calculate the equivalent circuit of R1, R2 prime S, okay, and maybe RC as well. First of all, RC is not actually an electrical resistance, okay, so it is put there to model the core loss component. Okay, so it is not a resistance that can be measured by a multimeter. Or similarly, yes, we have some resistance at the rotor bars, aluminum bars, so they have some resistance, and it can be represented like R2 prime over S. But again, if you think the actual structure of an induction machine, that rotor bars are not electrically connected to the stator windings. So even if you connect the ohm meter, multimeter to the stator terminals, they are not electrically connected, even if we show as if they are connected, because what we have is we just refer to those components and we just bring them into the same circuit, but they are not electrically connected. Okay, so what you will actually, if this is delta connected, and if you try to measure some resistances through here, so what you are going to measure is not only R1, but there will also be some currents passing through here. So the equivalent circuit, or let me, resistance between two lines here will be equal to, R1 parallel with R1 plus R1. So R1 path here, 2R1 path is here. So that one is equal to 2R1 divided by 3. And that one is equal to 0.29 ohm. So again, in some cases, you can just, disconnect one phase and you can measure the phase resistance directly. But it is usually easier to not, in a real case, not mechanically try to separate those things, but measures is like that. And you can calculate the actual phase resistance as 0.44 ohms. Okay, but that is if you are using a multimeter. This is just DC resistance. I mean, it's okay if you are not like really calculating really accurate. That is fine. But actually, another important feature is, yes, your ohm meter is measuring at DC, but while the machine is running, it is operating with AC. And remember, we have the skin depth, and we have the proximity effects, that kind of thing. So the current will not be distributed homogeneously in the those wires. So under AC excitation, the resistances will slightly go up. And if you want to really calculate it accurately, you need to know exact geometry and the diameter of those windings, blah blah blah. But as a rule of thumb, just as a one step accurate, it is again not 100% accurate, but you can estimate the AC resistance. We were doing the same thing with transformers. You can calculate in, again, this is just for 50 hertz or 60 hertz low frequency machines. So it is slightly more accurate to increase that resistance by 10%. Okay, then you can calculate that one. So R1 AC, which I will use in my calculations, can be written around like 0.48 ohms. Okay, so let's again, by the way, this line-to-line resistance is 2R over 3 for a delta connected machine. And if you remember, can be also connected like a Y connected machine. And if it were a Y connected thing, and if you measure that one, so in this case, resistance between two lines will be equal to, it will be just current will the current of the ohm meter will just flow through here. So it will be 2R1, so you can divide it by 2 and you can get the phase resistance. But our machine is delta connected. Okay, so now I have that resistance, and let me draw the equivalent circuit. In the Locked-Rotor case. Okay, so we can ignore the parallel branch. Okay, we have J2 prime, we have R2 prime over S, and S is equal to 1, so that is equal to R2 prime. We are applying some V1, and parallel branch is north. Okay, so let's try to calculate that one. So I can calculate the equivalent impedance, and I know the voltage and current. So if I divide, okay, voltage, again, don't forget this is delta connected and it will be different for a Y connected. Those are given as line voltage and line current. Again, draw it here. So you have delta connection. So V line to line is equal to phase voltage. So that's why I'm just taking the line voltage as phase voltage. I mean, all that equivalent circuit is per phase, and V1 should be the per phase voltage. And also here you have I line, and here you have I phase. In a delta connected machine, phase current is again not half, but 1 square root 3 of the line current, and it was the other way in a Y connected machine. So instead of just using line currents in a delta connected machine, I divide that value by square root 3. Okay, don't forget those things, please. Okay, so if you calculate it, let me write it here. So that equivalent is equal to 2.92. Okay, so I can also calculate the phase current. Okay, again, this is total input power, 6.4 kilovolts. So 6.4 kilovolts, kilowatts, sorry, divided by 3. That one is equal to, remember, the real power. Okay, the real power just dissipated through those resistances. Okay, the inductances and capacitors don't dissipate real power. So I can represent it like I phase square times R1 plus R2 prime. Okay, so that one, again, phase current can be written as like 77 amps divided by square root 3 times squared, okay, times R1 plus 2 square. And if you do that, R equivalent, or R1 plus R2 prime, is equal to 1.08 ohm is per phase. And I just calculated the R1 as 0.48. Okay, R1 is equal to 0.48 ohms. So you can write R2 prime is equal to 0.6 ohms. Again, this is not the actual resistance of the bars. Okay, if you somehow connect a multimeter to the bars, you will get a different value, but this is the referred rotor resistance to the primary side, and at the end of the day that will be more useful for our case. Okay, so these are I used these two parameters to calculate R1, and actually we also estimated the equivalent circuit, and I know that one. So let me write here. So Z equivalent is equal to R equivalent square plus X equivalent, which is equal to X1 plus X2 prime squared. Okay, or you can write X equivalent, which is equal to X1 plus X2 prime is equal to square root of that equivalent was 2.92 squared minus R equivalent was 1.08 squared. So that one is equal to 2.71 ohm. Okay, and again the usual convention is just, estimate R1 is equal to X1 is equal to X2, and I think that was given in the question, but I forgot, I think, copy to here. So you can assume X1 is equal to X2 prime, and that is equal to half of that value, so it is around 1.36 ohm per phase. Okay, so I estimate the series branch components using the Locked-Rotor test. Now I will use the no-load rotor test to calculate the parallel branch and other components. So here we have the no load test results. At the no load, I am applying now the rated voltage for 415 volts, and I am drawing some currents, and actually I am still getting some power, and some of it is due to the parallel branch RC component, but also in the question the friction and windage losses are given. Okay, even if you don't have any there are some electrical losses, but this is not the only losses. So 1.15 kilowatts of 1.65 kilowatts are lost in the mechanical system, so I need to calculate that value when calculating the parallel branch equivalent circuit. So anyway, let's start with that one, and let me try to draw again the equivalent circuit. So here I moved the parallel branch, the primary side. I have RC exam, I have R1, I have J X1, I have J2 prime, I have R2 prime over S, right? So then at no load, slip is around 0. If that one is around 0, that is infinite, so it is like open circuit. So that one is open circuit, and that current I2 prime is 0. So I have just RC and JXM for my components. All right, I can calculate the impedance at no load, okay, as V phase divided by I phase, and I am applying 415 volts. Again, this is the phase voltage, and 22.8 divided by square root 2 is my phase current, and my equivalent circuit is around 31 ohms. Okay, and let's try to calculate the losses, and again real losses, real power just dissipate through the resistive components here. So I P no load is equal to 1.65 kilowatt, and P friction is 1.15 kilowatt. So therefore I can calculate the P core at 415 volts for that volts as the difference between that one 1.15, so it is around 500 watts. Okay, half a kilowatt is dissipated through here, but again this is total loss. Okay, so I can calculate P core is equal to 3 times V1 square divided by RC. That is equal to 500 watts. Okay, so you can calculate RC from that circuit as around like 1033 ohms. Okay, and again, if you just go back, okay, and you can ask why we ignored the parallel branch here, because here R is around the equivalent resistance is like 1 ohm, and here you just have 1 kilo ohm, so the current in the parallel path around like just for the RC component is like 1000 times less than the series branch. So ignoring it just changes our results by around 0.1% accuracy, so which is not that important. Okay, so that is our RC, and I know the equivalent impedance as well, so I can calculate. Okay, so Z no load is equal to RC in parallel with XM. Okay, so and that one is equal to 31.3 ohm. Okay, so again, parallel calculations is not that straightforward, but I'm sure you can calculate it. It is 1 over, can go from conductivity squared 1 over RC squared is equal 1 over the no load squared, or you can get Z no load is equal to those things square root 1 over whatever. So once you calculated it, you will find xm is actually really close to that value. It is equal to 41,354. Okay, so that is 1000 ohm, becomes really small. And again, that is much larger compared to RC. They're much smaller compared to RC. So again, in some models, even RC can be ignored at all, and you can have just XM component. And XM again around 30 ohms, and it will be better if we include it in the parallel path. Again, it is the current, the resistances here is around 1 ohm, so you have a 30 ohm component, so the current is around like 1/30 of the other path. So ignoring that thing will cause around like 3% accuracy. Again, not big issue, but if you want to make it more accurate, maybe you can include it in the Locked-Rotor test and do your calculations accordingly. Anyway, so at the end of the day, if you just put those equivalent circuit parameters, it will be something that we draw branch here, just to give you an insight. So you have around 1032 ohms here. So J 31.54 ohm here, 0.48 ohm there, and J 1.36 ohm, J 1.36 ohm, and here you have 0.6 ohm divided by S. Okay, you have that equivalent circuit parameters, and for slip is equal to 1, that will be smallest, and as the slips get smaller, that value gets bigger and bigger, so it will changes how much power is transferred. Remember, it was the air gap power, so the value of the slip will change how much power is transferred and converted to torque, so which we will see in the following videos. Okay, thank you.